Hello, everyone. Thomas? I'm not sure here what's going on. There's no Thomas. Hey, wait a second. Look at that. What's
Hey,
happening?
Luca,
Haha,
how are
incredible.
you?
We've had this. Here's Thomas, finally.
Yeah, with only 5 seconds of rehearsal.
Yeah, did you enjoy this? Actually, Thomas visited me in Bergamo, northern Italy, for this fancy session, and yeah, very happy. So, what happens this week is that we'll work together. We'll have a few changes to be made in Thunder for the better, and not in the internals themselves, but in the way the project is set up. So, we're getting ready for some future event. So, we're very excited about that. And so, as part of that, I would say, today we'll talk about a topic that will be a popular topic in the months to come, right?
Yeah,
And what is
and
that?
now that we went all the long way here to meet, we have to reduce the accuracy. And so before we did like FP16 always, or BF16, and we did quantization. But now we want to have like the newest, the nicest floating point formats, and that it would be
Hmm.
FP8.
Yeah.
What do you think?
FP8. Okay. So I would say that we need to qualify what FP8 is. And so let's see, when you say reduce accuracy, kind of disappointing. Like, do I pay more to have less accuracy? What's going on?
Yeah, well, obviously, it has been a theme. Like you process less bits, you get more speed.
Yeah.
And so, obviously, this has been a thing that's been going on for quite a while. And so,
Yeah.
this FP8 actually is something that has been around for the Hopper things and has enabled quite a few things there. And also, it has been in ADA, so
Yeah,
yeah,
would be the L40, L4, all those GPUs that you find on Lightning Studios
yeah,
that you can use are ADA based and architecture based. And so you can use FP8 and try it out. Also because there's one architecture that is coming up, which is Blackwell, right? Um, and that has ample support for FP8. Um, and so we're kind of imagining that some of the bigger workloads will start using FP8 end to end. And actually, last week we talked about the DeepSeek V3
right.
report, and they one of the optimizations that they were using was a complete end-to-end training with FP8. And by the way, they were using both formats. Why am I talking about formats? Because FP8 comes in different formats. And
Yeah, so Luca's our low-level person.
oh
Let's
yeah,
say
for sure.
like where the bits are in FP8.
Yes. Okay. So
And
I've been trying to activate my scribbling window, which I forgot to activate before the show started. So now it's there, and I hope you can see it. So FP8. All right. So as we all know, or maybe not everybody knows, floating point numbers are not a thing that computers do, very elegantly, at least, because they're not analog computers, but they're digital. So they reason in bits, and bits are basically integer numbers. So they need to approximate what a floating point number is, and so they cannot represent all possible floating point numbers because we know there are infinitely many in a fixed interval. So it's, by definition they can do it. But when we say FP8, BF16, floating point 32, and so on, we talk about the number of bits that are used to produce an approximate or a floating point number that is somewhere in between where you need the floating point number to be. So FP8, well, sorry, you see, yes. So FP8, 8 stands for 8 bits. how are these 8 bits used? 1, 2, 3, 4, 5, 6, 7, 8. So floating point, if you look at the, oh, by the way, a nice story about floating point numbers is that, there are many ways of representing a number with a point in bits. And in the 70s, computer scientists kind of gathered around the table to understand how to build a floating point format that would be robust to people shooting themselves in the foot when doing operations, right? Because if you're multiplying a small number by a larger number, or sticking a floating point number into a sine or cosine exponential, like there's a lot of detail there that would make your calculation go completely trashed. And the IEEE, what is the number? I don't remember. Standard for floating point numbers in digital computers is something that came out of the 70s, but it was not the only one that was adopted at the time. And the story says the Ariane rocket that exploded, one of the incidents in aerospace in Europe, was due to a botched floating point operation that would be adopted if they adopted the IEEE format. So it can have a very real world repercussions.
Yeah, we don't know what the new computer did on the spaceship one, right?
No, yeah, exactly. Maybe it was a floating point. No, probably.
No, they say it was a hardware thing.
I know. All right. So anyway, so since there are many ways, let's take a look at what the FP8 way is. We have 3 parts in the floating point. One is the sign, let's say. One is the exponent, and I'll be vague here. Exponent, sorry, and then we have a mantissa.
Right.
And the mantissa is kind of a remainder floating point. The fractional, it's called the fractional part of a number after you do some operations, and it's used to encode the kind of the smaller numbers in the thing. So the exponent takes you to some level, and then you have a fractional number and you have a finite number of those fractional numbers to get to the point where you want to get.
Yes, so the mantissa, maybe if you read things, it's sometimes also called the significand. Yeah, and so basically exponent gives you the number of 2, power of 2.
Yep.
And then there's a 1 point something in binary, and this something is the mantissa bit.
Exactly. So in FP8, we have 2 formats that Hopper implements and also other generations implement. And they're called with a very explicit naming. So it's E4M3 or E5M2. And why are we going through all this? Because it's really important when you train something. So it ends up being very, very important.
Yeah.
So that's why we're explaining it the way the sausage is made, right?
Yeah, we could also say here that like FP16, that would be like E5M10, right? Because and that's the genesis of this E5M2 format. And BF16 by comparison would be E8M7, I guess, right?
Yes, M7.
And FP32 would be E8 7 plus 13, 23, right?
So we already see what's happening here, right? The mantissa is shrinking, the incredible shrinking mantissa, right?
Yeah, so my take on this story is like we had, and remember that FP16, that is a standard IEEE 754 format, just like FP32. People like figured out how to make FP16 work, and they needed this scaling thing in order to train a neural network, the loss scaling. And so, and then they thought, well, yeah, this is all complicated. And so they went to BF16, which basically avoids the loss scaling by having the exponent range that FP32 has. And then when it came to 8 bits, basically people thought, well, yeah, we figured out like FP16, so we can do with 5 bits of exponent. But for some things, this is kind of like hefty rounding, and so there's the E4 and 3 in addition, right?
Yeah, exactly. Because what happens essentially is that the exponent is a 2 to the x, right? So it goes, 2, 4, 8, and 16, and so on, right? And so it gets you in the ballpark of where we want to go, and it scales up. Whereas the mantissa is a fraction. And so the density of the points is kind of, at some point, goes kind of counter to the dynamic range you can reach. So a format that has, that goes up to very high number will have a lower density, and lower as large as the number gets, right? Whereas the something that has an exponent, less exponent and more mantissa will have a shorter range, but it will be a bit more dense. What does this mean? Oh, by the way, if you are confused because these two things don't sum up to 8, it's because we have a sign at the beginning, right? Usually you don't say S, E, blah blah blah. You just say E, and everybody quote knows.
Nobody invented floating points with 3 sign bits yet.
Yeah, exactly. Yet. So you have one sign bit there. The formulas are also kind of interesting, but maybe we don't get too much into them because it would take a bit too much time. But I think Wikipedia can tell you how to go from a sequence of bits into an actual number. We can do it, but
basically, I think one thing to also mention is that, and I'm always confused about that, like the exponent that has an offset, and basically what you do is that you center it around 0. So the basically, I don't know if the top bit of the exponent set to 1 and the remainder 0, that would be 1.0 or something like that. Or maybe it's like the top bit not set and on the other one's 1. But that's the usual thing, right?
So this is an example on how to obtain the FP8 number starting from exponent and mantissa. And so there's a sign, and then there's an exponent that you need to offset. It's called bias. And so the exponent is those 5 bits, so it's a binary number. So you extract the binary number, you subtract the bias, and then you multiply by that, and then you have this number here that gets you closer, that gets in between those jumps that the exponent gives you. And then this will be different, like this is M2, meaning when you have mantissa 2, this is a 4. If you have mantissa 3, it will be an 8, and so on. So it's very regular, and but you can look it up, and this is how it's
similarly, the 15 is like 2 to the 5 minus 1.
Minus 1, exactly. And so it will scale differently.
Well, 2 to the 5 minus 1, right?
Yeah.
You subtract 1 and it's...
Yeah, exactly. So anyway, this is great, but what you need to remember when you look at these things is that this is smaller range, higher precision, meaning you can express numbers that are closer together, and this goes the other way. And so when you train a neural network, you have a choice. Am I fine going, representing, cutting numbers according to range or not. So it turns out that, at least in theory, because then in practice now you start seeing people adopting different things, at least in theory, this one, sorry, I don't know why I changed my pen to something else. Okay, this one is better for forward. So for values themselves, so activations and so on. So you're running forward, you have activations, and you appreciate small differences, but you won't have crazy spikes. Although we know that we have outliers in neural networks, so yeah, but still, it's fine. When you optimize, though, gradients might assume very different values between themselves. And so magnitudes will be different. And so the recipe, the classical recipe, is to use this representation for the gradients and this representation for the values.
Yeah. If you want a rule of thumb, I mean, it's a lame intuition that it comes after the fact, but the gradients, it's the stochastic gradient descent, right? So there's noise in the gradients, and this noise means we don't care about the precision as much, but we will have like more wells with values.
Yeah, and so even if you're not very precise here, because after all, we have a mantissa of 2, meaning you have basically very few steps between one jump and the other jump in the exponential progression of the magnitude, then, basically it adds noise to the theoretical gradient, stochastic gradient descent, which is stochastic because you kind of choose batches. And this, accumulates further noise. The DeepSeek report that we saw the last week actually said that they trained everything end-to-end with E4 M3. And that's because probably they could regularize things in a way that didn't produce wide variation. And also they did a kind of a blockwise normalization. So basically when you need to create an so these numbers are centered, of course, if you have fewer numbers to express a quantity, then the best thing you can do, if you say you have a distribution of things that is distributed like that, whether you can represent it or not kind of depends on where your 0 is, right? So if your 0 is here, meaning you need to already use large exponents to get to this point, then you have very few, and the exponents are spaced in an exponential manner, right? So the next one will be much further away than the previous one. So the density decreases as you go large, meaning then the fractional part will have just a few points in between to represent your distribution. So it's much better to take your 0 to offset your distribution to be centered somewhere around here. So you'll have a lot more resolution in expressing small differences here, right? And so, and then of course, the more numbers you have, you just have one offset. If you have one offset for your whole network, which is kind of what you had in FP16, right? The whole model had just one offset, with a loss scaling. Loss scaling, exactly. It's not an offset; it's scaling. So, so that transformation is very poor, and so probably many things will get lost in translation here. And so FP8 and even more so FP6 and FP4, which are being introduced now, they need to be more and more granular with respect to where they scale around 0. So the fewer numbers you need to center, the better chance you have to properly represent that small distribution centered around that small neighborhood. All right, so we blabbering about this stuff, but it's really important because that's where the field is heading, and that's where the hardware is heading. We'll see more and more granular scaling and more tricks. And what does this give us is, GPUs that can train natively perform operations with core dedicated to instructions dedicated to this kind of low precision operations, and by as a consequence, faster and larger models being be trained. So it's a trend, and it's great to be on top of it. And so, what's our way to be on top of that?
Yeah. So actually, if you're obviously Luca and I were PyTorch people, and so there's two ways people currently implement FP8 with PyTorch. There's one thing called Torch.io, which is architecture optimization, and it's a project next to PyTorch, primarily driven by Meta. And there is another library that is primarily driven by the company that brought us Hopper and Ada and soon Blackwell with the FP8 support, and that is Transformer Engine. And so that is also great. And let's see. And there also is a start of a Thunder integration for that.
Yeah. So now we'll see something about that. So Torch.io, we actually released PyTorch Lightning 2.5 right about around the winter holidays. Yeah. And we added some examples on how to use Torch.io. Torch.io will decompose into operations that convert to these numerical formats, not just FP8, on others too. And then it will use Torch compile to fuse some of these operations. Transformer Engine comes with more kind of a more module-based approach. And so, yeah, please go check Torch.io. It's not yet integrated into Thunder. Probably will happen over the next few weeks or a few months. And then Transformer Engine already has an integration, so let's look at that this time.
Yeah.
So stop sharing here, start sharing there.
Yeah. The big move, right?
Yeah.
So let me share here my screen, and here we go.
Yes.
So this is the Transformer Engine website. It's an open source library on GitHub, which is very nifty. If you compile it in a Lightning Studio, and this one in particular, you need about 23 minutes unless you parallelize the build. But parallelizing the build is kind of tricky too, because I think it has some very large C++ files. So the flash attention is probably one of the C++ things that takes the most memory when you compile PyTorch, or also here for the Transformer Engine. But of course, this has like ample RAM, right? Just like the home computer. And so after you do this, you can do Transformer Engine, you can import it, and then you have...
You're not sharing.
Oh, I'm not. I'm not sharing the screen, but only the top.
Yeah, I think so.
Let me reshare then. Good that you looked. Maybe I just have. Yeah, I think I have several. I had the homepage open in 2 tabs. I'm sorry.
Yeah, no.
So here. So you can start the Transformer Engine, and I'm on an L40S, which is we can import Torch, right? It tells you if you look here, the environment. No, it's not here. Here it says what the things are. So it doesn't say. I don't think it says ADA here, right? Accelerator details. Yeah, you can get you get a link to the white paper.
Yeah.
And so it will tell you that it has FP8 in here. But yeah, so you can also check here Torch, CUDA, device, get device properties, I think. No? get device properties, and there you have like all sorts of properties. Actually, the property objects have more fields than seen here. But yeah, so but it's if you look at Transformer Engine, you have like common metadata PyTorch, and it is like a very nifty library, but it has lots of things to be aware of. And so at Thunder, we're trying to make it easy for you. So let's import Thunder too. And what did I do? Oh no.
This would.
Yeah, I looked at the files and I probably have this wood. Yeah. 557 probably at the bottom.
Yeah, here.
Yeah. You should never like chat while you have code files open.
Good thing that there was nothing particularly
nothing embarrassing. Okay, so all the latest on the upcoming products, but yeah, so let's have a MLP. So I'm a simple person. I can do this torch and then sequential, torch and then linear. And so one thing we talked about a bit is like that you need now multiples of 2 for your sizes. And Transformer Engine has some of these constraints too. So I'm just going to do a large power of 2 number of activations, and then we can use a relu activation if we're lazy, and then torch, and then linear again. And so this is our MLP model, but we should instantiate it on CODA. So with torch device, torch, and then CODA, we will have the model, and then we will have some input. And you know that I like to do it this way. So 512 times 1024. And so these are FP8 now, right? And so if I do M0 weight D type, it's float 62. And if we do, we can do a second module of the same type. I will do this for reference here. So mref and mref will have the same parameters. So we load the state data from M. This gives us the same parameters. But now we can compile torch with ThunderJIT M. And if we do nothing, we will not get Transformer Engine, because like lowering your precision is something that you have to ask nicely for, and it's not going to be a surprise. So we can use Thunder executors, Transformer Engine executor. Oh. Why does it not give me this anymore? Sometimes this can be very Thunder. You can't. Oh God. Default executors. Okay. Oh. Thunder has no attribute execute. Oh, it was the botched import probably because of the syntax error.
You have X, yeah.
And now I just need to figure out how this is.
Oh yeah.
Yeah.
I would rather change that X without underscore, or maybe not go X
Yeah.
at all. Yeah. This is part of the polish that we're gonna do.
Okay, so, and I need to select the transformer engine next to it.
This time with an underscore. Like, yeah. We need
Yeah. Okay, so this is our JIT module, and you see that it looks just the same. But now if we do JM imp, we see, yeah, there's numbers, and you see it's a float 32 tensor. But if you compare it to mref imp, you see that it's like very similar values, but not quite the same.
Yep.
And that is because this has been computing with low precision. And of course, we had the tools to like look in a bit more detail. And so one of our favorites to see what's going on was to just grab the PyTorch profiler. And so we profile like the call of jmimp, and then we print torch, prof key averages table, and we sort by self CUDA time total.
Yeah.
And
why are we doing that sort?
Yeah.
Because
because we want to like see what the largest are first, so I don't have to look that far. And there will be some double counting here, but let's not mind that much. But so the main thing I want to show you here is that we have this fine kernel. And you see here it's all E4 and 3. And that's not surprising because we only have the forward pass here. And now,
what does the you have A4, M3, F32, right?
Yeah. So probably like we have one part of the activation likely that is in lower precision, and we have the weight directly, right?
Yeah.
And we can
try also having bflow16 or flow16 model, because right now we created a flow 32 model. I'm wondering if we create that.
Let's do it.
Yeah.
All right.
Of course, we need to do something that we don't know what the outcome is otherwise.
Yeah, I mean, I always tell Luca this and this is what I tried out and it works. So way to go to ask for something different.
Spice it up a little bit.
Yeah. But of course, I know that Luca has a good laugh when it doesn't work, like in this case. Okay, so BF16 is not the favorite.
So what is the error here?
The error is expected AD type. So this is the Thunder checker.
Okay.
Saying, yeah.
So we are over.
Oh no, but this is because I have this.
Oh, the input. Yeah, exactly.
bfloat16, and then let's do this here too. bfloat16. This is
you
not the ideal way to do it. You
forgot the 16 and the second line, the input. Yeah.
No.
Object has no.
This
predict, yeah.
Okay, so this is a particularly clumsy way to cast to bfloat16.
Ooh, works.
But it works.
Yeah.
And so
now let's go there.
What are our things here?
And now I see. Before 16.
And this is part of what you get from the 23 minutes of compiling is that it has templates like for all the combinations of things, right?
Exactly.
And there's something F32 here too, which I'm not.
Which kind of tells us, it tells us something, right? And what it tells us is that the linear itself, if you had to lower it properly, like what Transformer Engine does, it would be a ton of, not a ton, but quite a few operations because they're is type demotion, promotion, whatever happens there, and then it fuses, like these kernels are already fusions of sets of operations that need to happen. This is a bit different than compared to Torch.io, which kind of exposes more of these operations and lets Torch compile take care of that in real time.
Yeah. And if we look at the backward, we can also see that there shows up like the real wide stuff. Like we have E4 and 3 from the forward, and we have E5 and 2, which is now in the backward, and we have the BF16, which is likely the wake. And so you have all sorts of things showing up here.
Yeah, because this is the backward, so
this is the forward and the backward.
Exactly.
The
combination of two. And so you have certain numbers that are represented in one. So when we said before, the backward will use E5 and 2, it was kind of a slur. Like the gradients are represented that way, but the backward will be a combination of multiple data types that will produce gradients that will be represented that way.
Right. And here we have like what is in the module. We have, it's a normal linear here. Oh no, the source code says linear, and it gets translated to the T linear. And
look at that. You have a T3, right? The MV fusion.
Yeah, and you have the MV fusion
with a B8.
Oh, the B8 is the Boolean. Comparison. And then you have
let's cut this one.
And then you have the T linear 5. And one thing you see here, which is different than in the quantization, is that you have two different calls here, T linear 4 and 5. And the reason is that you have these scaling factors that you don't see here. So this keeps the state in the T linear, which is all nice, but obviously it would be even neater if we could like make
it out, right?
More explicit what's going on there, because you now have a side channel to the backward, right? If you look at Thunder, last backward traces, and look at, I always manage to change this all the time. You have the backward, but somehow, like, you don't see, you have a little bit of a side channel here in the context, likely, for the transformer engine. And we will need to get into this in more detail. There's also like TE sync for the backward, and we will want to know all about that, but maybe not like right now.
I think we're pretty much on time. But this was great. The first foray into FP8, and it will be big in 2025. So we start with something that will be very actual. Our goal is to make things run on the latest architecture. So Thunder is a unique opportunity for us to really optimize for the latest architectures, and we'll see more of that moving forward. So this intro to FP8 was fun. So let's do more. All right. So anyway, thanks for sticking around, and see you in a week with the fruit of our work together.
Okay. See you. Bye-bye.